Dr. Viviana Acquaviva, an astrophysicist with a strong interest in data science, but also a faculty member and associate professor at the physics department at the City University of New York and the CUNY Graduate Center. Welcome to the Data Exchange Podcast.
Thank you so much, Ben. Thanks for having me.
Yeah,
I guess I should say I am actually a full professor as of yesterday.
Oh,
so we can
awesome.
Celebrate together my new title. Nothing changes. I don't think I even get a raise, but hey, you know.
But that's awesome. That's great.
Thank you.
All right. So first question. So our conversation will be basically the applications of ML to physics, but also the intersection of the two fields. So first question to you is, Jupyter Notebooks just celebrated its 20-year anniversary, and it was actually created by two graduate students in physics. So looking back at your graduate school years, to what extent were you using ML at the time? And by the way, before you answer, at the risk of dating myself, I have a PhD in math, and back then, actually, we were still using the phrase data mining.
Well, oh no, I think I can beat you on that one because, I feel like I'm in the generation where you don't want to write what programming languages you've learned in grad school if you're applying to jobs. So I think I can definitely relate. I mean, I was thinking about this, and in a way, I think for academics, we never afraid to date ourselves because all of our data are public. So I got my PhD in 2006. Right. And I remember, and I started in 2002. And before that, anything that I had done was pen and paper. And so my, what here would be called the master thesis was like this traditional thing with pen and paper. And then in grad school, I was very grateful because one of my advisors basically told me, you need to learn some programming. And this was already, it was putting me at an advantage. And I can now confess, I think like the language that was quite used at the time was Fortran.
So the implication here is that you had data.
Well, we work a lot with simulations. We did have a little bit of data, though. Like I was working in observation, like in cosmology, and so we did have data. And I picked up things like Markov chain Monte Carlo methods, and this was great for me for finding a job. But I can tell you, I was like one of the few people I was considered advanced, just because I could code these things in Fortran.
Now, I have to say that I also came of age when actually the exit strategy was not data science. If you wanted to leave academia, it was Wall Street.
Yes.
And there it was physicists and mathematicians, right?
Yes.
So they valued in terms of maybe we can teach these people programming, but they have the chops to learn programming, but maybe they can take it a step further. So so you were doing simulations. At what point did the whole ML phase come into the fray?
Yes, very good. So this was, let's say that, after my PhD, I moved to the US, and for a while we were doing this sort of like statistical inference, like traditional things. And then, as typical, I did like a couple of postdocs. And in my last semester as a postdoc, which was spring 2012, I actually asked my supervisor, is it okay if I take a grad course in ML in the computer science department? So this was just something where, I had a feeling that it was interesting. I'm also a person who gets bored very easily. So I was like, I need to learn something new. And I knew that, starting a faculty job and getting more into teaching would have been more difficult. And then a couple of years later, I was actually determined to leave academia. And so the reason why I got a bit more into it in 2014 was just that, I just couldn't see myself doing, something over and over for the next, 20, 30 years. And I really thought of ML as, my exit strategy, even at the point where, people already consider them, like the bottleneck is over with. So I was already on a tenure track position. So I did, like the Coursera ML course, just like everybody else. Started doing Kaggle competitions just to, get a sense of whether I would be
So
competitive
so
somehow.
this was all during when you still had your physics job.
Oh
And
yeah,
by the
yeah,
way, so Viviana, just for
yeah.
some context, would you classify yourself as on the theory or experimental side?
Oh, definitely not experimental. Like you never want me close to anything like a lab. I mean, even even when I was an undergrad, all I could do is like, go and pick the resistances. I could recognize the colors, and that was my only skill. So
So you started taking courses and Kaggle competitions,
yes.
and then let me guess, you came across the quote, the best minds of my generation were optimizing models for ads.
I didn't. I wonder what would have been my path if I had. No, I think just what happened is that I mean, in the meantime, like I also had the kid, and so I think that sort of like slow down my eagerness of going for something different, but also gave me time, I think, to starting using these tools in my research and with students, and that somehow opened a new world for me. And then I realized that, you know what, I think I really still love what I do, and I really like that I'm able to use new things. And I also realized the potential of maybe teaching these things to physics students. And so overall, I never know if this is my final answer. If I still feel that sometimes I'm like, oh, I need to do something new. But I think for now I'm quite happy actually with how things are
So
going.
so now you are a theoretical physicist using ML. How
Right,
unusual
an
are
astrophysicist, I would say, yeah.
yeah, how unusual are you?
Because oh no, I am. I used to be quite the unicorn, and I think now I'm. I guess like a role similar to mine is quite common. In fact, where I'm talking from is the Center for Computational Astrophysics of the Flatiron Institute, and this whole institute is actually sponsored by the Simons Foundation.
Oh, okay.
So you
Yeah, yeah.
may actually, you probably heard of Jim Simons
Jim
since
Simons.
we
Yeah,
were
yeah, yeah,
talking
yeah.
exactly.
Turn Simons invariant.
Exactly. And so, like I think he was like probably like the most eminent physicist who actually made money in the financial industry. And I
Yeah,
think
yeah. Mathematician.
fair enough, fair enough. Yes. I think we always want to claim them, but I think you're right.
um, so
And
so so now then, what is the typical project for you? So like, who are your collaborators?
right. So I feel like, people here are sort of like, just like a community of people who have like, a physics, astrophysics background, but it's actually a bunch of centers. And then like, really strong computational interest and ML. I'm actually, I'm wearing this badge of this like ML across the universe workshop where I'm at. And so it could be, I mean, I guess it's different people, but, I work like, my physics work is mostly in galaxy evolution. So, like we try to understand, how galaxies form and evolve and what mechanisms matter. And so a lot of times, for example, someone like me could collaborate with someone who understands a bit more about the physics of these things. And, we try to get together and see, okay, like they may have a problem to solve. Say, I don't know, what is the role of merging galaxies in, our picture of galaxy evolution? And, like I may think about, okay, like what could be a good way of going at it, given the data that we have, the simulations that we have.
So before ML, what would have been the path?
Right. So the nice thing that we have now is that before ML, we had to do everything with traditional inference, which basically means that every time we do forward modeling, like every time we have to come up with some sort of model of an observable quantities, we need to go from, the initial condition, like the parameters we need to measure, all the way to observable. Like I'll give you an example. Say that, we want to measure, I don't know, like the age of a galaxy. Then, and like in the data that we have are some observation of these galaxies, say some pictures. Then in order to be able to like make some conclusion on how old is a galaxy, we need to what we would do is to say, okay, let's say that I know how to make a model of a galaxy for various ages. I can look at how the model looks like.
So here, model means in the classic way of writing down equations.
Right. And the model is actually, like I need to be able to simulate how the observed galaxy would be at different ages. And this is the thing that is very difficult, right? Because these objects that we work with, like galaxies, are extremely complex. So in order to say, okay, like I need to write down, like, or to come up with a picture of a spectrum of a galaxy of a given age, you basically take a very complex system, you simplify to what you, the physicist, think that is important. And of course, this comes with all sorts of biases. And then you still have to, like sort of make that simulations for many values of the age of the galaxy. And then you will pick the one that looks most like the data. And you would say, okay, like, I guess that, this is the age that, fits the data best. And so this is like something that is one, extremely time consuming, right? Traditional inference in many parameter spaces is quite time consuming. But I think most importantly, you pick what variables matter. And I think this is the really nice things that ML gave us, is a tool to learn representations from data. So, and I think this is really, one of the parts that I'm most excited. Now, we can, first of all, we can work with data at the image level much more simply. And then, we can just sort of like study them and try to see if we can learn representations that are useful without, us saying, oh, I think that, these 5 numbers are what we need to measure. So I think this is cool.
So at the level of techniques, then you're using kind of the similar techniques that people in industry are using, deep learning for computer vision.
A lot of it, because it's a very visual science. Astronomy in particular is a very visual science, right? And so we have a lot of sequences. So we have lots of like time series data, and we have lots of images.
And then because you're scientists, everything has to be reproducible. You have to share your data. And so now, is there an accepted workflow or set of tools for validating someone else's ML-driven paper in physics?
Yes, and I think actually, again, this is something where I think, like, especially astronomy is very open. I think the standard now, like our data are very often public, especially big data, right? We have these common observatories. And so typically, like the data themselves are often available. And now I would say that the standard for publication is sharing your code. Right, if you don't, I think as a referee, I would personally be very wary of code of, papers that don't share their code, don't have like a GitHub, don't have, something that makes them reproducible. And I think this is actually the standard in the field.
I share my code, but you can't run it.
Well, resources is a different aspect, isn't it?
Yeah.
Yes. And this is actually something I'm really worried about. But yes, I think transparency also means that you are now expected to share your code. We have like new journals that are just for publishing code. So I think this is quite good.
So what's the difference between someone in graduate school now and when you were? Like, what kind of classes are they taking that you weren't taking?
Yeah, I mean, well, first of all, I sort of don't envy graduate students nowadays, because I feel like they have a lot more pressure, and especially someone in a field like this. I think now they are held to impossible standards of needing to know the state of the art, both like in physics, astronomy, and in computer science. And I think this is becoming quite a problem, just because how much we are asking them to learn. And I think, for example, I started teaching this machine learning for physics and astronomy class at the undergrad level a few years ago. And now, I've taught it at graduate level a few times. So I think we have things like, computational methods. We, in my college, actually in undergrad, we started teaching quantum computing. I think, like all in general, sort of, data analysis is, for example, something that I never had.
So whereas before, like you said, you had to consciously teach yourself how to code. Now it's expected, how to code.
it's expected that you know how to code. I still don't think we teach it enough. And I think one of the reasons is that, you know, because we, who are the people who are supposed to teach, you know, often don't know anything about that. I still think we have a problem. But yeah, I think there are many more like data centric classes that we certainly didn't have. And maybe, you know, there's still like, you know, the theory classes are still there, but I think at least there's a bit more variety in the curriculum the students can pick.
So in terms of your work, objectively speaking, set aside that you love ML. So how much of your recent work would have been possible without ML?
That's a good question. Well, I assume that we're talking about research work.
Yeah.
I don't think I'm, you know, as much as I love ML, I really love the idea of just, you know, adding these tools and making them standard. So if I look at back and, you know, like my last couple of papers, one of them was sort of like straight up statistical inference with like Bayesian techniques. So, you know, like no ML to be seen. And the other one was ML driven, but not quite ML, like it was about something, you know, as I mentioned, I think one of the things that we have to do in astronomy is to learn from simulations a lot, just because we have only one universe. We can't really, you know, create more. And so we rely a lot on simulations to see how the universe works. And then one of the problems that we have, especially with these ML methods, that we don't have any ground truth, right? There's nobody who really tells you when this galaxy was born or, you know, like how many stars it has or things like these. So I've thought a lot about, okay, you know, like if you train your model, and now I'm talking about an ML model, so it's relevant, but tangentially on simulations, what would it take for you to believe it on data? And so I think this is, you know, similar to a domain adaptation problem, but not quite, because I think really what you're having here is that you may learn a different relation on simulations just because your simulations are not perfect. And so trying to understand, you know, like what would happen if you apply this on data, I think it's something that should be possible to describe in terms of the difference, like some sort of like distance metric between simulations and data in observable space. But I think, you know, we don't have, I think, you know, any of the standard distance metrics won't cut it. So I've been thinking a lot about, you know, what makes sense, you know, like how can we build something that measures how well simulations and data match so that then we can apply ML models that are trained in simulations and not come up with things that are completely absurd or, you know, being overconfident of how well we're doing.
So you're also writing a book for Princeton University Press on machine learning techniques for physics and astronomy.
Yes.
So what are some of the key chapters? Let's forget the fact that the book is still in progress. Let's assume the book is finished. What would have been the chapters?
Well, yeah, fair enough. I mean, it is reasonably advanced. I think the topics are really standard. And, you know, I felt like, you know, I tried to go with really foundations. So I think the real question is, why did you need to write another book, given that, you know, like the things that I talk about, you know, classifications, decision tree, KNN, you know, naive bias, you know, support vector machines, random forest, you know, neural nets. You know, why do we need another book? I think is the questions.
What about reinforcement learning?
Very good, very good. But I don't quite get there. I think, you know, what I feel like the problem is that for me, when I set up for this book, I really was targeting the beginner
right.
Students and their instructors. Right. So I think, you know, the target of this book is like sort of like, you know, senior undergrad, maybe early grad students. And I also wanted to provide some resource for instructors where people, and, you know, like I see, I'm getting, just the last week, I got 3 requests from colleagues who are now tasked with teaching this type of courses, but they never had any formal training. And, you know, my choice was to stay with these sort of like simple foundational things, because otherwise I feel like your book will be outdated in a year or, you know, actually within the time you're writing. So I do agree with you that reinforcement learning, self-supervised learning, in general, anything that is unsupervised or semi-supervised is what's most important for astronomy? Is this what is like state of the art, and will we have opportunity for the biggest progress? But this is really just meant to give some solid idea, foundational things, so that students can go and then look at the many resources that they have and being able to take advantage of them.
So is it fair to say that most of the time you work with images?
In astronomy, I think images are common. For me personally, I haven't worked much with images. I tend to work with spectra, which are sort of like, so a reduced, well, it's a different technique, right? So in images, you literally take pictures. And in spectra, what you do is just like you measure the luminosity of an object with a very fine resolution in wavelengths. So you separate, photons, which is what we measure. You separate them very finely according to their wavelength. And then you make a little chart of luminosity versus wavelength that is like very detailed.
I see.
And I think these are sort of like, similarly common.
What volume of data are we talking about? Is it terabytes, petabytes?
Right. So I think, in things until now, I think we were, like terabytes. I feel like, for example, like the Sloan Digital Sky survey that has been, like one of the most successful survey of the last 20 years. I think, like each data release was of the order of like a few or perhaps a few dozens of terabytes. But now, like our next big ground observatory, which is the Vera Rubin Observatory, which is slated to begin in 2 years operations, they will have 30 terabytes of data each night.
Wow.
And
so you really need distributed computing.
Yes. So we have, all sorts of issues. We need that. We need like, for example, one of the things that we are putting a lot of emphasis on is things like real-time anomaly detection. So we have all of these like, time domain events, like millions every night. We need to be streamed without 60 seconds, because if you find something super interesting, you want to be able to take the other observatories in the world and point them there.
You don't want a lot of false positives.
You don't want a lot of false positives for sure, but you don't want a lot of false negatives either, because that's the exciting part.
Right.
And so, I think we're facing a lot of new challenges.
So a lot of the challenges, as you pointed out, might become computer science and systems challenges.
Yes.
Yeah. I have a framework for you. Ray.
Oh, tell me about it.
Ray. Ray.io. Yeah. It's written in C++, but it's just has a Python interface, and it's becoming very popular. And basically, you can use it for all sorts of it's basically distributed computing made simple.
Okay.
Like
I like the made simple part.
Yeah. Like I have code that runs on my laptop. I add 2 lines of code. Boom, I'm in a cluster.
Okay. That sounds actually pretty good, because I think one of the things that we have as scientists is that we never have any training in, like how to write code, how to do distributed computing, like how do we even begin to think about these things?
What about, Viviana, what about text? So the classic text mining examples, or even some of the early scientists with going into machine learning, they would go and mine the scientific literature for trends and topics. And so this is not something you guys do?
I don't think so. I have used this sort of like as a, like term project for a course.
Yeah.
Things
but
like, finding reviewers, sort of finding, papers. But I'm not aware of any of these efforts, on a more substantial level.
Yeah, because there are definitely parts in science where people are able to do text mining and information extraction and maybe identify a key molecule or whatever, right?
Oh,
so I don't know. I guess in your case it really doesn't apply, because your problems are not or a different.
I guess our data are almost never in text form.
So when I think of machine learning and physics, the first thing I think about is astronomy. But what other
Yes.
parts of physics is ML, based on your conversations with your colleagues? What other areas in physics is ML disrupting physics?
Well, I think particle physics is something where, like now all, they have these like particle colliders, like you may have heard of these like large hadron colliders. And so I think a lot, and they are really looking for like needles in haystacks. And, either because they're looking at very, very vague traces of, like possibly a particle that has been creating for a moment and then has disappeared in a series of products. And these events are very rare. And so I think they've been using machine learning with great success in terms of like, simulating events and try to understand what techniques, what pipeline they had to put together. And so I think this has now become the standard also for analyzing data. Is like, they have all of these jets that show all these like particles that have been produced. And then, you want to estimate, well, whether or not this came from, like a certain process of particle creation, collision, and then I can't think of the word, decay. And so I think for them it's actually quite relevant.
Now, we've been talking about ML's influence on physics. What about the reverse? How is, when you talk to ML colleagues, are there ways where you think you've kind of influenced their way of thinking?
That's a great question.
I have an example here, by the way.
Well, tell me the example, and then I
So
will tell
actually,
you if it resonates.
the previous episode, the episode I just aired last week, which would have been August 19, was basically with Charles Martin, who's actually a computational chemist, but he works with machine learning people in Berkeley who are ex-physicists. So they started applying ideas from statistical physics to study deep learning models. So basically, and I'll send you a link to their paper. Basically, they have a way of evaluating models without access to the training data by just looking at the weights of the models. So random matrix theory, but they have code, and so it's a little more practical. But that's an example where I think they took ideas from their original field and are trying to kind of influence the field they're in now.
Yeah, I think that's really cool. I don't have like similar examples, but in part it's also because I don't really get to talk a lot about, like with colleagues who are outside academia and more in the ML field. I do think that, like we, of course, get a lot of training in problem solving and thinking about things like, like what are the uncertainties that are involved in this? How do we think about, how our choice of architecture matters and what does it mean for the results that we get, what things we can trust. And so I would imagine that these type of skills are something that will be helpful, even if, you're building a model for some like other completely different application.
Yeah, the rigorous thinking. I know in grad school, I went to grad school in Santa Barbara, so a lot of physicists.
Seems like they're everywhere in your life, these physicists.
Mainly string theorists, actually.
Oh, wow.
But what I do know, what I recollect is that they are really good at making really long calculations with a lot of precision.
Yes.
Yes. And so,
attention to detail is definitely.
Yeah, I know, but I mean, they can do exact calculations up to many decimal places, right?
Yes. Absolutely.
But I don't think that matters when you're serving ads or recommending movies.
No, but I think, the idea of thinking rigorously and, like not taking shortcuts, I think, hopefully is helpful.
So let's close by, I want to just rattle off some high level trends in ML and see how get your reaction. So last year I talked with someone from MIT, and they had just published a paper on the computational limits of deep learning. So basically,
I see.
the idea is that, we have these models, large language models, large computer vision models. We can get them more and more accurate, but at a cost, right? So a cost economically, because it gets getting more expensive to train the models, environmentally, and so on and so forth. So how about in your field? So are you seeing kind of diminishing returns in terms of some of these models? So you get to the point where, okay, maybe in order for us to get to another level of accuracy with these models, it's just going to get more expensive, and we've run out of grant money, right? So.
Yes, I think the answer is not yet, but I think we are close to this point. And I think, we have several problems. One of them, the one that I'm actually most worried about, is the fact that because the resources that we need to do state-of-the-art things are, like notably increased. Like I feel like 5 years ago, they've been completely confident that any grad student with a laptop or, access to Google Colab or whatever, like something very limited, was able to do meaningful research. And I feel like this is already not the case anymore, at least, if you want to work in a data intensive aspect of astrophysics. And so I'm really worried that in the end, these resources will be so unevenly distributed that we will create like a huge, access inequity. So this is something that I am worried about. And I think, this is something that as a community, we should take care of. We should, go to our funding agencies and just like make sure that there are resources that are, specifically meant for people who are not at rich institutions. Then to go back to your actual question, which is, will we see diminishing returns? I think we are close to that point. And I, not necessarily because we will hit, the accuracy that we can have, but I think maybe the problem will be, again, we have exploited the data and now it's time to go back to the theory and make better theory models.
I was just going to say that maybe it's time to come up with some other clever.
Yes,
right? So.
Yes. And in a way, I feel like this would be like good because, like we also had this hype and, I support it, but I'm not, like as an enthusiastic supporter, as you can imagine. It's not that I feel like, ML should, is a substitute for science. Yes. And so I think, I'm expecting that, like the wave will come down and then, we will have maybe something which is a bit more balanced.
So then, you have to make sure your grad students don't come back to you 10 years from now and you tell you, hey, we spent all this time learning ML.
That's true. But that's why, I emphasize the science part in my book. Sometimes I honestly feel like when I'm writing, I feel like, am I shooting myself in the foot? Because I just told them that feature engineering is much better if you use your domain knowledge rather than, like this giant machinery. But I think that's why I think we need to do both.
So the other thing that's come up a lot in industry is this notion of ML ops, which basically productionizing models and things like that. Now, you folks, you're in research mode, but on the other hand, you are running scientific experiments all the time. So maybe there is a reason for you to deploy models in production that are constantly running in background, right?
Yeah, I think this is something that we still don't know how to do. Only like the biggest missions, the biggest observatories finally now have positions open for people who know how to do this. And, it's still like not commensurate to the need.
Honestly, industry is still grappling with it. I mean, many of the more advanced teams have tools and processes in place, but a lot of teams are still struggling with it.
Okay, yeah, I feel like I'm sure that we are still further behind. I feel like literally this is, this type of positions, I've seen them advertised like, just in the last couple of years. But I think the, sort of like the average research group will have like no one who can actually take this role because of lack of qualifications, but even more so for lack of time, because this is not something that is rewarded in academia. So this is another thing that needs to change.
So the other thing that's happening again in industry is kind of the rise of specialized systems. So you mentioned anomaly detection.
Mhm.
So for example, time series databases
Right. Yeah.
are back in a big way in industry. The other actually data type that's popping up a lot now, Viviana, is graphs. So you've got
Mm.
graph databases, graph neural networks, and so on and so forth. Are you seeing that
I've seen, I mean, I have to say, like, I'm
in
actually
physics?
not
I mean, in
at all
physics.
an expert, but
Yeah.
this workshop where I'm at, which is like a cosmology workshop, is the first one where in the title of talks I've seen graph neural networks. And there was actually, I mean, this is like, a special place. I think, here we're really seeing things as they happen. And so I myself have never, yet like like in my own field of galaxy evolutions, I haven't seen a paper like that, but I think cosmology people are starting to
And
use them.
and then the final kind of mega trend is that I wanted to bring up is the whole responsible AI, which is really an umbrella term around managing risk, which includes, fairness,
Yes.
explainability, interpretability. Well, actually, it's something that you folks,
Environmental footprint.
yeah, but something that you folks might also be thinking about is safety and reliability. Or on the other hand, maybe it's the people in other fields of engineering. I always have this joke where I tell people, this ML is cool, but would you ever fly a plane using reinforcement learning without knowing without injecting some kind of domain knowledge of aerodynamics and things like
Right.
that. So safety and reliability in certain domains is super critical, right? So self-driving cars, right?
Right. Or the medical field,
Yeah,
right?
yeah,
I
yeah,
mean,
yeah,
would
yeah,
you
yeah,
believe a diagnosis made by a machine? Even,
yeah, yeah, yeah,
yeah.
yeah. So are these things are any of these aspects of responsible AI things that you also have to grapple with?
Yes, I think in a way, I mean, I think in terms of like ethical uses, clearly, like as a scientific field, like in which there is no money to be made, we are shielded by many of these considerations. But I think we do have, I think equity concern for me. One is the one that I already mentioned. I think, very uneven access to resources. The other is the fact that just because the machine learning trend is moving so quickly, I have a feeling that a lot of people are being left behind. Right. And so this is going to impact their research careers, like even their, like ability to read papers. And we don't do enough to teach these things, to make them available. And so I think this is, like access barriers and, like access to resources are the aspects I would say are most important, like at the moment, like crucially important in my field.
By the way, Viviana, one of the things that I thought was a good, in fact, they are good trends, is the rise of some of these online sharing sites like Archive, right? So that means I can be in the Philippines or somewhere, I can read papers, but
Yes.
then GitHub, same thing, right? So I can download
Yep.
the code. But then I guess as we discussed earlier in this conversation, this is great. I can read the papers, I can download the code, but I don't have any compute,
Yeah.
right? So
Yeah. I mean, there are, like small things that are available. Like, I think Colab is like, it was like a nice thing, where, something that everybody can access
yeah.
for free. And, like if you don't have like, a big computational job to run, is sufficient. But yeah, that's definitely a concern. These and the fact that resources also needs to be widely available and tailored. So something I'm doing here at this institute this year is taking the class that I teach and turning into a MOOC, one of these, like mass open
Oh man,
online course.
that's a lot of work, right? Isn't the rule of thumb for every hour you have to spend like 5-6 hours?
Yes, but I made this choice 10 years ago, Ben, when I started teaching. So I feel
I
like,
guess the nice thing about the MOOC is once you invest that time, then that thing
yes.
just keeps playing, right?
Right, exactly. And so I feel like this is better than, since I basically teach this every semester.
Yeah.
I felt like, but the idea would be like to offer it for free, because when I opened it in the spring, I had like an overwhelming response. And so, like there were a lot of people, of students, that I had to say no to, just because I also feel like to keep the conversation alive, having too many people, even just on Zoom, was too much. And so I figure maybe, like this will help. And then the other things I'm trying to think about is taking all these materials that I developed, which are already available for free, like, notebooks and slides and whatnot, and lectures, and start translating them in other languages.
Well, so in closing, so the good thing about ML, like we pointed out, the papers are free. A lot of the code is open source.
Mm-hmm.
Is that true generally in physics? Because we on the outside hear about these kind of gated paywall, behind the paywall scientific journals.
No, the tradition with papers has always been like, I can't remember the year the archive was founded, but I think like every single physics and astronomy paper has been on the archive like since day one. So maybe, like some people would only put it after it's published, but in general, every paper is accessible. And this is actually something that I don't find in other fields, like in computer science, for example. I don't find it's always the case. So that helps. And the data, I think, different communities are better. I feel like particle physics, big experiment, they tend to have their data, only accessible to collaboration members. But I feel like in astronomy, there are a lot of free data, just because, there are so few telescopes.
So in physics, for every 100 GitHub repos I visit that's tied to a paper, how many of them will actually run?
Oh, I have no idea. What's your guess?
I don't know. I have no idea.
No, yeah,
I do
don't
know. I thought actually, I had a great conversation with a couple of Italian professors who are doing research on recommender systems.
Oh, I see.
In a previous episode of this podcast, and so what they do is they were studying, how good is neural networks for recommenders, and they found mixed results. But part of the challenge is like they were saying, someone will publish a paper, they'll put up a GitHub repo, but they couldn't run the thing, right?
And why?
Or I'm not sure exactly. Yeah.
It was like the data was not there, or just the code wouldn't run.
Yeah. They could.
Maybe that's a new trend.
Or they could run it, but they couldn't reproduce what was in the paper.
Oh, I see. Well, that's much more worrisome.
Yeah. So that has to change generally.
Yeah, it hasn't happened to me personally, but yeah, that would be something I would be a bit concerned about.
Yeah. And with that, thank you, Viviana.
Thank you so much, Ben, for having me.
And congratulations on becoming a full professor.
Thank you so much.
What a milestone.